In kinematics using integration, we're going to be concerned with motion in a straight line. As a result, we need two types of functions. One is the displacement function, and the other one is velocity function, known as vt. So given the displacement function, we can find the velocity function by differentiating the displacement function. And given the velocity function, we can determine the displacement function using the integral. So we will write the displacement function is equal to the integral sign of the velocity function in respect to time. So we will use this integration to determine the total distance traveled. So let's take an example where a particle P moves in a straight line with a velocity function, which is described by t squared minus 3t plus 2. And it's obviously evident that this is going to be a quadratic function. So the first thing we need to do is to determine any changes of direction, and that can only happen when the velocity is 0. Therefore, 0 is equal to t squared minus 3t plus 2. We can only find out if we now factorize this. So we're going to factorize this quadratic. So the particle will change direction at t is equal to 1 and at t is equal to 2. But which way it's going, we need to do a sign diagram. Okay, so the particle will start moving at time is equal to 0. At time is 1, it's going to change direction, and it's also going to change direction at time is equal to 2. So from this equation, we can find out that the sign diagram will be positive between 0 and 1, negative, and positive after t is equal to 2. This was done by substituting maybe 0 into this equation here and finding that it is positive, and a number between 1 and 2 into this equation to find that this is negative, and so on. So since the signs change at 1 and 2, it means that the particle is traveling to the right for until 1 second, and then it changes its direction and is traveling back, and then it changes its direction at 2 seconds, and it changes and keeps on going to the right. But to determine how far it travels in the first 4 seconds, we're going to have to look at the displacement function. And this can be done only by integrating the velocity function, which happens to be t squared minus 3t plus 2. And we're going to integrate that with respect to t. That is t cubed over 3 minus 3t squared over 2 plus 2t. And we always have to now add that constant of integration c. So now that we've got our displacement function, we should find out where our particle was at the origin. We also should look at it when it was at t is equal to 1, and also when it was at t is equal to 2. That's when it changed also direction. And finally, when it after 4 seconds. Okay, so substituting these values for t here and here and also here, we should get a value for here as c. Substituting 1, and we should get 5 over 6 plus c. Substituting 2, we should have 2/3 plus c. And substituting 4, we should get 5 1/3 plus c. And these are the positions in our motion diagram. So we need to now draw that motion diagram by drawing a line, and we'll start off at position C. Now here we go, moving along for 1 second only, and we get up to, and after 1 second we know from our sign diagram that the particle moved left again, and it stopped 2/3 plus c. After 2 seconds, the particle changed again signs and started moving to the right. So after 4 seconds, our interest, it stopped 5 1/3 plus the c constant. So to find out the total distance traveled, we'll need to calculate the distance from C to 5 over 6 plus c. Then we'll need to calculate the distance from the blue distance going left, and then we need to calculate the distance from there to there. So all in all, we've got 3 sections. We've got we have a red part section. We also have the blue section going backwards, and we also have the last section that we need to calculate those distances. And you will see how the constant c disappears in each case. So in the red section, we've got a distance of 5 on 6 plus c, and we need to take away c from here to here. So we're going to take away c. Now with this, that's this part. With the second part, we are looking at this small distance from here to there. So we'll say 5 over 6 plus c, take away 2 over 3 plus c. And our last distance covered is the one from 2 on 3 plus c all the way up to 5 1/3 plus c. And we need to add these distances up so that we can find what the total distance is. So for total distances covered, you'll find out that the constant of integration should always cancel. Have a look here. You've got plus c, take away c. These two will cancel. You have plus c here, and that negative will cancel out this c. So these two c's will cancel out, and this plus c will cancel out with this c. So all in all, we can cancel these out and rewrite this equation again. So that's the total distance is 5 over 6 plus 5 on 6, take 2 on 3 plus 5 1/3 minus 2/3. And I'll change most of them to the denominator 6, so that will be 4 over 6, and minus 4 over 6 plus 5 1/3. I'll leave that alone. So I have 2 over 6 plus 5 1/3. That's 1/3 plus 5 1/3. giving me a total of 5 2/3, and we're talking about meters. If you are asked to find the total displacement, then that is going to be the final position, take away the original position. And the final position that we had was at S4, and the original position was at 0. So all we do is substitute that 5 1/3 plus C, take away C. And that just cuts out the two C's, and our answer is just 5 1/3 meters. And we should say to the right, because displacement is always vectorial, and it tells us not only the magnitude, but it tells us the direction.